Hi everybody, how are you doing today? Hope everybody is safe and well. We're going to continue to move through chapter 3, which is solving systems of linear equations in two variables. We've covered 3.1 and 3.2, and now we go to 3.3. And 3.3 is solving a system of linear equations in three variables. The primary variables that we're going to be looking at will be x, y, and z, but it really doesn't make too much difference which variables have been chosen when we're looking at the system. Now, the means of solving a system of linear equations in three variables is to use elimination. And so we're going to take a look at problem number 1 right here just so that you see what the system looks like. It's a system of three equations. They're all linear equations, and they contain the three variables, x, y, and z. Now, item number 1 that we want to mention is if a system has a solution, it's going to take three values to make the solution. A value for x, a value for y, and a value for z. And we call this solution an ordered triple because it takes three unique values of x, y, and z that will satisfy or be a solution for all three equations. And like I just said, the means of solving a system of this type, we will use elimination. So let's go through the steps of how we do it. Step number 1. You choose a variable that you want to eliminate from the entire system. The choice is yours. You can eliminate x, you can eliminate y, you can eliminate z. But since we are looking at elimination to do it, and when we're using elimination, it involves adding opposites to get rid of the variable that we want to get rid of. Let's take a look at this system and see if there is maybe a clue up there that would let us know which variable might be the best of the three to eliminate. People, I want you to look at equations 1 and 2, and I want you to look at the variable z. In equation 1, we have a negative 1z. In equation 2, we have a positive 1z. If we were to take equations 1 and 2 and eliminate z from those two equations, we wouldn't have to do anything to either side of the equation. We could add the left-hand side and add the right-hand side right away, and the z's would cancel out, and then we could move on to our next step. So step number 1 in solving a system of linear equations in three variables is to identify the variable that you want to eliminate first. And so I'm going to eliminate z from this entire system. And so here is the means of eliminating z from this system. You start out by picking two different pairs of equations. Two different pairs. And what we will do with each of those pairs that we identify and write down, we're going to use the process of elimination to eliminate the variable z from the overall system. So definitely one pair of equations that we'll write down will be equation 1 and equation 2, because the coefficients of z for equations 1 and 2, they're opposites right now. And we'll just simply have to add down, and they will get eliminated immediately. So, in this area right here, right about in this spot, I'm going to copy down equations 1 and 2. X plus 4y minus z is equal to 20. That's number 1. And then number 2. 3x plus 2y plus z is equal to 8, and we'll call that number 2. And then over in this vicinity right here, I'll pick a completely different pair of equations. I can no longer pick 1 and 2. I'll either have to pick equation 1 with equation 3 or 2 with 3. And folks, it doesn't make any difference. So I'm going to go ahead and pick 2 and 3. And we'll just situate those right over here in this area. 3x plus 2y plus z is equal to 8. That's number 2. And then number 3. 2x minus 3y plus 2z is equal to negative 16. Now, I believe it is wise. I'm going to double check just to make sure that everything has been copied down correctly, because many mistakes are made because we copy information down wrong. So I just want to double check equations 1 and 2 that I've done. X plus 4y minus z is equal to 20. That looks good. 3x plus 2y plus z is equal to 8. That looks good. This second one, equations 2 and 3. Equation 2, 3x plus 2y plus z is equal to 8. And equation 3, 2x minus 3y plus 2z is equal to negative 16. Both pairs of equations look good. So now we go back to this first pair, equations 1 and 2. And again, we're going to eliminate z from this pair of equations. And because the coefficients of z are already opposites of one another, we don't have to bring in multiplication whatsoever. We can bring the line down, and we add down. 1x plus 3x gives us 4x. Positive 4y added to a positive 2y is a positive 6y. Bring down the equal, because the z's go, add the 20 with the 8, and we have 28. So you see, the message is, you identify the variable that you want to eliminate, and you take any two different pairs of equations from the entire system, and your goal is for each of the pairs of equation to eliminate the variable z, because that's the variable that we picked. And when it gets eliminated, you're going to be left with a linear equation in two variables. And I'm going to take that 4x plus 6y is equal to 28, and I'm going to situate it right up here. 4x plus 6y is equal to 28. And now we're going to go to this second pair. The objective, eliminate z from the system. This second equation has a coefficient of a positive 2z. This has a coefficient of 1z. If we were to multiply both sides of equation number 2 by a negative 2, let me just kind of put that right there so you can see what I'm talking about. If you multiply negative 2 times this z, that's going to become a negative 2z, which is going to be the opposite of positive 2z, and the z's will go. So we're going to multiply both sides of equation number 2 by a negative 2. So we'll put a negative 2 there and a negative 2 there. Here we go. We'll distribute. Negative times positive, a negative 6x. negative times positive, a negative 4y. Negative times positive, a negative 2z is equal to negative 2 times 8, a negative 16. Draw the line. Take this middle equation and we'll add it to the bottom one. 2x added to a negative 6x, a negative 4x. Negative 3y added to a negative 4y is negative 7y. The z's go bye-bye. The constant terms, we've got a negative 16 coupled with another negative 16. That's negative 32. Now we take that negative 4x, negative 7y is equal to negative 32, and we'll write it right below this one that we had obtained when adding both sides of this first pair. So we've got a negative 4x, a negative 7y is equal to a negative 32. Now just so that there's plenty of room, folks, I'm going to erase this. I want to make sure that I've got room. So now we'll take this brand new system of two equations in two variables, and our immediate objective now will be to find the values of x and y. And once we find the values of x and y, we'll then be able to take those two values and substitute those values into any one of these original three equations that we started off with to find our value of z. Z will be the last value that we will find because it was the letter that we eliminated from the entire system. So we come and we take a look at this system, and we notice they've been very kind to us just by the way that the numbers flowed. The x terms are opposites of one another. We again do not have to bring in any multiplication involved, because a positive 4x coupled with a negative 4x will go. So we can just immediately draw our line, and we'll end up, when adding down, to get a negative 1y is equal to a negative 4. Now divide both sides by negative 1, and we'll get y is equal to a positive 4. Not that I have to do it right now, but I am going to get it ready. The solution to a system of linear equations in three variables is a ordered triple, with x written first, y written second, and z written third. We just found our value of y is 4. Now we'll take the value of y, which is 4, and we will substitute that 4 in place of y in any one of these equations. It doesn't matter which one. I'll go ahead and take the top one. 4x plus 6y is equal to 28. Bring down the 4x. Bring down the coefficient of 6. Make a house. And in place of y, put the value of y that we just found, which was 4. That will equal 28. Do the mathematics. 4x positive 24 is equal to 28. Negative 24, negative 24. 4x is equal to 4 over 4 on both. X is equal to 1. Put that 1 in the x spot of that potential triple that we're about to get. And then I'll just go ahead and erase this. And now we'll take those two values, that being x and that being y, and we'll substitute both of those values in to any one of these equations. Let's just go ahead and take number 3. Even though number 3 might have a little bit more information in it, It's right there. It doesn't matter which one we go with. We'll pick number 3. Double check that you've copied it down right. Now let's substitute the value of x and the value of y into this equation, and we'll be able then to find our value of z. 2 times the value of x, which is 1, negative 3 times the value of y, which is 4, plus 2z is equal to negative 16. Positive 2, negative 12. Positive 2z is equal to negative 16. Combine like terms. They're like. Negative 10, positive 2z is equal to negative 16. Positive 10, positive 10. 2z is equal to negative 6. Over 2, over 2. Z is equal to negative 3. Stick that negative 3 in the z spot. The ordered triple is 1, 4, negative 3. If you want to make the check, you can take that ordered triple and substitute those into each one of these equations just to verify that it is true, but we're not going to do it. I think we have a good answer for this particular one. So that's the basis of solving a system of linear equations in 3 variables. Needless to say, people, you need to make sure that you give yourself plenty of room. Don't try to cram in the work in the nooks and crannies of a sheet of paper. It's not going to go. You're defeating the whole purpose. It's easy enough to make a mistake when you are giving space. So you have to be very, very careful about what you're doing. The mathematics is basic, but you have to be careful with your steps and what you are doing. Now let's take a look at number 2. There is a reason for it. Number 2, it looks like this. 2y minus z is equal to 7. The second equation, x plus 2y plus z is equal to 17. And the third equation, 2x, negative 3y, positive 2z is equal to negative 1. Now let me just double check. 2y minus z is equal to 7. X plus 2y plus z is equal to 17. 2x minus 3y plus 2z is equal to negative 1. It looks good. Now you can see the difference between problem 2 and problem 1. On problem 2, the very top equation, equation number 1, does not contain the variable x. Well, then that should be the variable that we should eliminate from the entire system. We would have more work in for us if we were to eliminate y or z from this system. We could, but it's more work. X is already missing from equation number 1. So I'm just going to take that equation number 1 right now and write it off in an isolated spot. 2y minus z is equal to 7. Now we will take equations 2 and 3 and eliminate x from those 2 equations. This one, he's already settled. I've got him written over there. Let's get rid of x. This coefficient is 1. This coefficient is 2. 2 is a multiple of 1. We can take both sides of equation number 2 and we can multiply both sides by a negative 2, because negative 2 times x is negative 2x, and that's opposite of a positive 2x. So let's do the distribution. negative 2x, negative 4y, negative 2z. And that is equal to a negative 34. Distributed. Negative 2x, negative 4y, negative 2z, negative 34. Let's draw the line. The x's go, and just because of the nature of the numbers, the z's are going to go as well. That doesn't always happen, but it happened here. I just randomly picked this problem. Oh, the x's go. Negative 3y coupled with a negative 4y is a negative 7y. And the z's cancel out. So negative 7y is going to be equal to a negative 35 over negative 7 over negative 7, and y will be equal to a positive 5. So we got y's value to be 5. And I'm going to make this ordered triple right about here. It's kind of close by me. Y is in the middle. We'll stick that right in there. And all we then have to do, you see what we thought we would be getting here. By getting rid of the x's, we thought that we would be getting an equation that would contain both the y and the z like the very first one did. But it didn't, and it makes our work much, much easier to do. Now that we know that y's value is 5, we can now take that value of 5, which is the value of y, and substitute it into this equation, and we'll get our value of z. So bring down that coefficient of 2 and make a house. And in place of y, 5. Minus 1z is equal to 7. 10 negative 1z is equal to 7. Negative 10, negative 10. Negative 1z is equal to negative 3. Over negative 1, over negative 1, z would be equal to a positive 3. Stick that right in here. There's your z. And now we'll just go to any one of those equations. There's nothing wrong with this item number 2, this equation number 2. So I'm just going to do a little bit of erasing. What you might have to do is actually copy down equation number 2 again. But I'm just going to kind of use it right in this area right here. X plus 2y plus z is equal to 17. We need x, so we bring down the x, plus 2 times the value of y, which is 2 times 5, plus the value of z, which is 3, is equal to 17. X, positive 10, positive 3 is equal to 17. X plus 13 is equal to 17. Subtract 13 from both. X is equal to 4. 4, 5, 3, the solution to the system. Again, they were very kind on this one. I just arbitrarily picked it out. But it worked out very, very nicely. Now, one other one that we want to deal with, and the thing that we want to share is I'm getting this third one set up. Every now and then, you might end up with a situation to where the solution to the system is a unique solution. A unique solution would be that you can have an infinite number of solutions to the system, or you can have no solution to the system. It's not the common trend, but it can happen. So here's number 3. X minus 2y plus 4z is equal to negative 10. Second equation, negative 3x, positive 6y, negative 12z is equal to 20. And 2x, positive 5y, plus z is equal to 12. Just want to double check it with number 3. X minus 2y plus 4z is equal to negative 10. Negative 3x plus 6y, negative 12z is equal to 20. 2x plus 5y plus z is equal to 12. Now you step back and you look at it. You have to make up your mind first of all, which variable do you want to eliminate from the system? Doesn't make any difference. You can pick x, you can pick y, you can pick z. It doesn't make any difference. Let's just go ahead and pick x. It's that first one that's right there. And let's copy down the first 2 as one of our pair. X minus 2y plus 4z is equal to negative 10. That's number 1. Number 2, negative 3x, positive 6y, negative 12z is equal to 20. That's number 2. And let's say that we pick for the second pair, just to have it written over there, let's pick number 1 and number 3. You could pick 2 and 3. You just can't pick 1 and 2 because we've already done it. So if we pick 1 and 3, that'd be x minus 2y plus 4z is equal to negative 10. And then number 3, 2x plus 5y plus z, and that's going to be equal to 12, and that's number 3. Let's go back over here to this first pair, just like we did on problem number 1. We're going to get rid of x. He's a negative 3x. I want this puppy to become a positive 3x. He will if we multiply both sides of equation 1 by a positive 3. So tuck it, and let's multiply both sides by 3. That will give us 3x, negative 6y, positive 12z, and that will be equal to a negative 30. And we will now notice the middle equation and the new one that we just obtained. If we draw the line, not only are the x's going, but the y's are canceling out and the z's are canceling out, and that's unique. They cancel, they cancel, they cancel. We're left with nothing but a 0 on the left, and on the right we add the positive 20 with the negative 30. That's going to give us a negative 10. And this rule is the same rule that we find out when we're solving a system of linear equations in 2 variables. Rule: if during the process of elimination, if you lose all of your variables and you end up with a numerical statement down at the bottom that is false, and this numerical statement down at the bottom is false because 0 does not equal negative 10. And because 0 does not equal negative 10, the solution to this entire system is the empty set or no solution. You don't have to worry about going to him. It was already settled by looking at this pair. We lost all of our variable terms, and we ended up with a numerical statement that was false. 0 does not equal negative 10. That indicates that the solution to this entire system is no solution or the empty set. Now folks, if we would have had a situation here where it would have been 0 is equal to 0, or negative 10 is equal to negative 10, that would have indicated that we would have had an infinite number of ordered triples that would have satisfied that system. But that was not the case on this. Okay. So we'll call that kind of part 1 in this 3.3. There's 2 other problems that I want to do, and they're going to be application problems, and we'll treat those in a few moments. You take care of yourself right now and be good, and we'll talk to you later. Bye.